Okay, so with our talk about Taylor polynomials and using those to approximate functions, we're going to now use them to go into our next topic, 8.8, which is power series. So I've mentioned power series before, but it was very brief, so let's refresh our memory here. We want to expand our discussion of the series to the case where the terms of the series are functions of the variable x. So the primary reason for studying series is that we can use them to represent functions. Some functions can be represented exactly by an infinite series, which we would call a power series. When written out, a power series looks very much like an infinite version of our Taylor polynomials. Okay, so a power series, or let's look at the definition of our power series. So if x is a variable, then an infinite series of the form, the sum of n equals 0 to infinity of a sub n x to the n, is called a power series. More generally, series of the form, the sum of n equals 0 to infinity a sub n times x minus c to the n, is called a power series centered at c, where c is a constant. Okay, a really common power series is for the function f of x equals e to the x. Write that down here. Okay, which is, let me write it down here, is the sum from n equals 0 to infinity of x to the n over n factorial. So the difference between the series that we've kind of been talking about already and the series that we're moving on to now is now we're talking about functions of x. So before, all of our series were kind of in terms of n. We still have that, but now we're adding in that function aspect where it's in terms of x. Okay. So that's the big difference here. We're changing to be talking about functions now. So to kind of see this same pattern here, let's write out the first four terms of this power series listed here. Okay. So we're starting at n equals 0. So the first term we would have negative 1 to the 0 times x to the 2 times 0 over 2 times 0 factorial plus negative 1 to the first, x to the 2 times 1 over 2 times 1 factorial plus negative 1 squared, x to the 2 times 2 to 2 factorial plus negative 1 to the third, x to the 2 times 3 over 2 times 3 factorial. Which when we simplify, we get 1 plus negative x squared over 2 plus x to the fourth over 4 factorial, which is 24, plus x to the sixth over 6 factorial, which is 720. So the difference between our normal series and this power series is now we have that term x in our series, which looks a lot like our Taylor polynomials. No, well, if I could spell polynomial. okay, or is similar to our Taylor polynomial, which is what we just finished talking about in 8.7. So let's talk more about these power series. Just like other series, we can have convergence or divergence of a power series. So for a power series that is centered at C, precisely one of the following statements is true. The series converges only at C. There exists a real number r greater than 0, such that the series converges absolutely for absolute value of x minus c less than r, and diverges for x minus c greater than r. And the series converges absolutely for all x. Okay. So the number r we call the radius of convergence of the power series. If the series converges only at C, then this radius of convergence is 0. If the series converges for all x, then this radius of convergence is infinity. The set of all values of x for which the power series converges is called the interval of convergence of the power series. So really what we're talking about here is there's 3 different ways our function, right, because we're representing a function here, can converge as a series. We can have it converge at a single point C. That's our first option. And this is our number line x. We could have it converge for an interval about C, where, the interval is r on each side of C. And then our last option is that it converges along this entire line. Okay. So really what this is kind of describing is the domain of this. Okay. So we're talking about the domain of f, which is the set of all x values for which the power series converges. Okay. So that's really what we're talking about here, is a domain. So you can have convergence at one point, you can have convergence across an interval, or you can have convergence on the entire x-axis, or for any x value. Okay, so how do we test for convergence of a power series? We use the ratio test. Okay, so in order to check to see if the series converges only at C, you would use the ratio test. So we would set up our n plus 1 over n ratio. And if we find that the limit as n approaches infinity of your ratio is infinity, which normally would mean that it diverges, right? Okay. Then we know that our series converges only at our point C, which, remember, C is your center. Okay. Also remember that this means your r is 0. Your radius of convergence is 0 because there's no interval around C that includes any other points for which it converges. Okay. So in order to see if there exists a real number r such that it would converge absolutely for some interval around C, okay, our solution we're going to find is going to look like this, what I just highlighted. We're going to find some, our answer looks like the absolute value of x plus or minus some constant.